Good morning. Thank you all for being here. It's amazing to be back in Berlin. So, in the last few years, lots of things, the way we interact with machine and thinking of image processing or speech recognition, there have been amazing enhancements. So what happened? And usually when I want to understand what happened, the first thing I do is I start by looking in the past. So, okay. So has anybody saw this picture before? So this is a picture I love. This is the London Underground in 1939, and this is people counting by hand something like 4 million tickets to build a sort of a model and a prediction of how the underground was going to be used in the next few years and plan for the future expansions. So I love this kind of heroic efforts, and I think now with the instruments that we have today, the tools that we have today really have no excuse in improving our customer experience using the data and learning from the data. And that was an example of having data and building a prediction. And to do that, you need to build a model. And the data can be the 4 million tickets of the underground, can be an audio file, and you want to predict what's the text inside, what's the intent of this text. And to do that, you want to build the model. The model is the part that is decoupling the actual data from the predictions you want to build, so that you can predict on new data that you still haven't seen. And how can we build the model? So if we continue to look back, we can see like in 1959, there's Arthur Samuel. He was one of the first person to write a computer program that was playing a game. He wrote the game of checkers. Probably chess was too complex for the time. And at first he was interested in exploring the space of the solutions in an efficient way. Then he also had the idea of having computer programs fighting against other computer programs to learn and improve their strategy. And at the end of this process, he created a computer program that was much better than him in playing checkers. And I think this is a great example of machine learning. And machine learning is quite a broad topic. We already saw something today. And there are a lot of subtopics. For example, there's supervised learning. Supervised learning is the most common subtopic of machine learning. Is when we want to create a model, we want to infer a model from labeled data. So for example, the tickets of the underground, we know everything about those tickets. We know the time and the number of people that was using the underground, and then we want to predict these same values for the future. There's also unsupervised learning, is when we don't have labeled data, but still we want to understand the data. Maybe we want to find a hidden pattern inside the data. For example, if you have a large company with 1 million customers, you can't know all customers one by one, but maybe you want to understand what are the kind of customers that you have. Maybe there's customers that are at risk of leaving your company, there are customers that are new, customers that are old, and you want maybe to understand them better. And then there's a third part that is a little bit in between supervised and unsupervised learning, is reinforcement learning, is when you want to perform a goal in a dynamic environment. And for example, here we have the classical example is self-driving cars, so driving a vehicle, and also playing against an opponent. And I think there's a panel after the break, so you will hear a lot about reinforcement learning. It's one of the hot topics because it's where lots of investments now are. For unsupervised learning, the classical example is clustering of data. So when you have data points and you want to cluster these data points together, this is something that goes back probably at least to the 80s, and it's the examples that I was doing about customers. Lots of companies, they want to cluster their customers together to understand if there's categories of customers that they can interact in a similar way. In this case, if we want to group these data points, it's very easy. Visually, we see that there are 3 small clusters. But this is a very basic example with few data points and 2 dimensions. Normally, you have maybe hundreds or thousands of dimensions, all the possible characteristics of a customer, for example. And you can have millions of those data points to cluster. So it's much more complex than this basic example. Another example of unsupervised learning is topic modeling. Is when you have a large corpus of documents and you want to understand what are the top topics that are described in these documents. And there's lots of algorithms to do that. Normally, the idea here is to look for infrequent words that are more frequent in these documents, and this is giving you a signal that's the topic that this document is about. And there's also a very nice open source tool here. It's for Python developers. It's called GenSim. So if you want, for example, a nice experiment that you can do is export all your emails, maybe business and personal emails into separate repositories, and then run this tool and see what are the top topics that you talk about in your business emails and in your personal emails. It's a nice test to do. For supervised learning, the three main categories are regression, when you want to understand and forecast and predict a numeric value. For example, if you run a bike sharing scheme in a town, maybe you want to know how many bikes will be rented tomorrow so that you know how many bikes you can replace or during a day without disrupting your service, or if you have to plan for buying new bikes. Binary classification is very common, is when you want to classify in two categories, like true or false, yes or no. And most email clients, they incorporate binary classification to try to understand if an email is a spam or not. And usually they use your feedback to improve the classification. Normally, these binary classification algorithms inside, they have some kind of confidence that is expressed as a percentage. Part of the creation of the model is to define a threshold. So if the classification predicts that this email is spam with 55% probability, then if you are above this threshold, then it's spam. If you are below this threshold, it's not spam. And usually this threshold is also deciding how much false positive or false negative you get. And depending on your use case, false positive or false negative can be good or bad. For example, if you're predicting illness in medicine, then it's better to have a false positive than a false negative, because a false positive can be diagnosed better and solved. A false negative, then you lose the possible classification, and probably the person thinks it's not ill, but maybe there's something that must be investigated better. Multi-class classification is when you want to go beyond two simple classes. For example, in sentiment analysis in the past, people were just looking if a tweet or a social comment on Facebook was positive or negative. Now we can enter into the details of the sentiment, so to understand if this is happy, sad, angry, confused, disgusted, surprised, calm, and so on. So we can classify among more categories. And there's a very easy trick to implement multi-class classification is just to do binary classification on all the possible classes. So is this happy or not? Is this sad or not? Is this comment angry or not? And then get the one with a higher level of confidence. So it's very easy to transform a binary classification algorithm into a multi-class classification with this trick. And with supervised learning, the idea is that you want to create this model. We say we want to train the model. And to train the model means that you want to create a model that when you apply this model to build prediction on the labeled data that you have, labeled because this is supervised learning, you reduce the error that you obtain. So you want to find the parameters that will reduce the size of the error. Actually, there's a very important step when you build a model, that's to validate the model. Because if the model works well with the data that you have, this is not important. You want to build a model that works with the new data that you still haven't seen. So how can you validate a model to work on new data? The idea here is that you want to avoid overfitting. So let's imagine that this is some data that you have. Let's imagine from the bike sharing scheme that I was describing before. And this is the number of bikes that are rented in the early morning here in Berlin. So if I create a very complex polynomial model, then this is a perfect fitting for my numbers. I'm fitting the data points perfectly, and if I try to build a prediction, I get something strange. For example, that in the very early morning, I need more bikes than after some time. And the idea here is that probably the model is too complex, and a much better fitting would be a simpler linear model. And what happens to be true is that normally all data that we collect in the world contains error, so we shouldn't look for perfect lines that fit the data. We should look for data that, for simple model that can fit our data. And if we compare the prediction of this model, we see that we get very different prediction from the simple linear model compared to the complex polynomial model. So how can we decide which of the two models is good? So the idea here is to take all the data that we have, for example, the 4 million tickets of the underground, or maybe thousands of audio files where I want to build my speech recognition model, and split the data in two. So usually 70–80% of the data is what I use for the training, to train the model, find the right parameters that reduce the error on this training data, and then keep 20–30% of the data on the side, and then apply the model on this new set of data that has never seen the model before, and measure the error on this validation set. In this way, I can understand if the model that I created on the training set is capable of abstracting and working on new data that has never seen before. So validation with this approach is really a core component of of building a model. But we're here because there have been great advancement in image processing, speech recognition, and the models that we build in this area are quite different because we use a different technology. We use neural networks. And neural networks is not a new topic. Actually, the first examples of neural networks start in 1943, so this is McCulloch and Pitts. And at the time, when we were building a computer, we were physically building the AND and the OR. So that there were like logic units, physical AND, physical OR, that were connected together with cables. And they had the idea of creating a threshold logic unit. So a logic unit that instead of what an AND or an OR does, you could connect multiple logic units together, and if you get lots of signal, lots of ones, so true in Boolean logic, then this logic unit will fire an output as yes. If you get lower than a certain threshold, then it's a no, it's a false. And this was trying to simulate how the neurons of our brains work, because that's the basic simplified model of our neuron work. They are all connected, there's lots of connections, and if you get more than a certain threshold, then the neuron will fire an output. And this simplified model was then refined over the years, and Frank Rosenblatt, he wrote this very important paper, The Principle of Neurodynamics, where he created the abstract concept of a perceptron. It's the idealized version of a neuron for building predictions. And the idea of a perceptron is very simple. You have your input data, so it's an array of numbers. Then what you do, you multiply all this input data with each data has its own weight. Then you sum all those numbers together. And then you go through a nonlinear function. It's called an activation function. Normally has a shape like this, even if there's lots of different functions that can be used. And then you get an output. So normally, if the sum of all the inputs multiplied by the weights is greater than some threshold, you get some output, even though now we use quite different activation functions. One thing that is important here is that the activation function is not linear, and we will see why this is important afterwards. And then if we put everything together, we see that this is actually just a building block that we can use. Unfortunately, what happened is that a few years after, two other very important people in artificial intelligence, Marvin Minsky and Seymour Papert, they wrote a very in-depth analysis of how these perceptrons work. And they found out that they can solve only very simple problems. Technically, linearly separable functions can be approximated by a perceptron, but something more complex, even just a simple XOR, an exclusive OR, can't be implemented in a perceptron because it's beyond what the perceptron can do. And that slowed down for lots of years the research in neural networks. Also because people try to have the idea of, okay, our brains, they don't use a single neuron. We can use multiple perceptrons together. So we can create an input layer with multiple perceptrons. We send the data there. And then the output of these neurons is connected to another layer of perceptrons and so on until we get an output. And this would work, but it was very complex for the time. It was very complex because the number of parameters was exploding, and there was no efficient algorithm to train and find the right parameters, the right weights to fit the labeled data with this model. In the 70s, we started to have this algorithm. It's called backpropagation. So the idea is that from the front, you go back and find the right values to fit the output. But it was very complex. But in the meantime, two things happened. One is that processors, they get much more powerful. This is Moore's law. So in the 70s, a single CPU was having a few thousand transistors inside. Now we are in the range of the billions of transistors. So we have much, much more power that we can use to to train and create these models. And also, we have to thank everybody who is playing video games. So has anybody played or is playing video games here in this room? Yeah? No, I would expect more. Basically what happened is that to render the graphics of video game, a different kind of processor was created, what is called the graphical processing unit, the GPU. And when you create and render graphics, you don't need a single powerful core. You can do everything in parallel. So the GPUs are different from a single CPU because instead of having a few very powerful cores, you have thousands, for example, in the last generation of NVIDIA processors, thousands of cores that you can use all together. There are even now specific cores that can do some basic linear algebra in hardware, so like the tensor cores of the latest generation NVIDIA processors. And this is the same technology that from video games moved into other areas, such as in building machine learning models. And in the same time, it happened also that we have there's been a lot of research, so the backpropagation algorithm was improved. We learned how to apply this in a highly scalable environment using GPU processors. Usually a GPU is 10 times faster, roughly, than a normal CPU. So if a training with CPU would take 1 month, the same training with GPUs would take a few days, just to give you an idea. So now we have the technology and we have the algorithms to do the training. And what happened is that we start to build these deep networks, and that's why we now talk about deep learning. And we also start to do strange things on how we build these neural networks. So for example, to do image processing, we actually do something slightly different than normal. So this is how you would fit a picture to a neural network. Normally, if you give just the numbers, it's very difficult to get a good result from a neural network. Because when you transform these pixels into numbers, you lose all the information on the locality of the pictures. You don't know if there is a line, if there is a circle. You just send numbers to a neural network. That's very complex for the neural network to handle. So the idea is to use something slightly different, and it's what is called convolutional matrix. And this is also called image kernels in image processing. The idea is that you can take a small matrix, like 3 by 3, 5 by 5, 7 by 7, and move this matrix on top of all the pixel of the input image. And then you multiply the pixel and the surrounding pixel by the numbers in this matrix. So this is not matrix multiplication, it's something different. And this is an example of an identity here, because I'm taking the central pixel by multiplying by 1 and disregarding all the surrounding pixels. So this is completely useless. But if I change this number a little bit, and I use, for example, this one, I can look for left or right edges in a picture. And now you can see that I can start to extract very easily information that can be much more useful for the neural network to understand if there is an edge or not in a certain part of my picture. And if I continue, I can look for top, I can look for bottom, I can even give random numbers and still get a different perspective and a different kind of information is extracted from my picture. And this is actually what we start to do. And it's what we normally call convolutional neural networks. So the idea is that you take a picture, then you create this matrix, you use random numbers. Those numbers will be parameters that you need to find with the training. And then we get all different versions of a picture, not just one, but multiple versions. And then we continue to do this multiple times. And at the end, we use fully connected layers, as we saw before, to get the final classification and, for example, understand what's inside a picture. And this approach of CNNs is very good with pictures, but actually works every time we have an ordered set of data. So it works also with audio files. So whenever you have a set of data where order in 1 dimension or 2 dimensions or more dimensions is important. And what happened is that before the introduction of CNNs, it was very difficult to understand and predict what was inside a picture. Imagenet is an open classification challenge where universities and private companies, they all work together and try to get the best results. And in 2010, 2011, we were at around 25–30% error rate in classifying an image. That means that 1 prediction out of 3, 1 prediction out of 4 was wrong. That basically means that predictions were useless. Then in 2012, CNNs were introduced, and you can see the drop of the error. And now we are In 2017, we are 2.25% error, I think. There's people that is thinking that we are probably overfitting for the specific Imagenet use case now. But the idea is that now we can do very good, we are very good in understanding and classifying pictures, and we are approaching human error. Actually, this graphic is important also in this perspective. When you measure error from machine learning, it's not like when you measure error in other areas. Error is what must be compared to human error. As soon as you approach human error, then things become very much usable because they behave as we expect from another, if a human was involved. And there are still lots of challenges here with machine learning. There's lots of data is required, so to build models with images or audio files for speech recognition, you need petabytes of data. Training is very complex, you usually need thousands of GPUs to build a model. And also, when you build a model, you need to run the predictions. And to run the predictions, you need to transform this model that was a batch operation into something that you can serve online. Because if you build a bike sharing prediction application, your customer, after the model is built, they will expect to get prediction in milliseconds. They don't want to wait 20 seconds for a mobile application to give an estimation of something. So you need also to have this very fast prediction side. And to give you an example of the size, this is a university in the US. They use AWS to build a model for natural language processing. It's the example of topic modeling that I did at the beginning. They use basically all the academic magazines available since the 50s, and they build a topic modeling model, and they used at the top 1.1 million of virtual CPUs together to build and elaborate this model. It's an incredible scale. And in Amazon, we have thousands of engineers that works on these kind of problems since the beginning. If you look at the Amazon homepage in 1994, we already talk about recommendations and suggestions for customers. And we use machine learning in our fulfillment center and for optimizing the logistics with the robots that we have in our warehouses to help you search on the website, for improving existing products, and also to create new products that would not be possible without machine learning. You heard it. Maybe we can increase the volume a little bit. So Alexa said hello. So you know Alexa because it's available in Germany. Alexa is completely built on top of deep learning so that we can do automatic speech recognition and natural language processing and understands the voice and match that with the intent, and then you can use this to customize and create your own intents. The Amazon Go is a shop that we have in Seattle. It's in beta. It's available only for Amazon employees now. And it's a shop where there's no cash. So you get inside, you pick up what you want, and then when you get out, you receive the bill depending on what you pick up. And of course, the first time I was there, I tried to collect 3 bars of chocolate, put them in the bag, then I took one, I put it back. I tried to do all these kind of things, but everything worked and I received the correct bill. So we use a mix of cameras and sensors, and we use machine learning to understand what the people is getting in their own bags. And we saw lots of customers do amazing things here, from Slack to financial institution like FINRA, that is using machine learning for classifying images. This is an example of how we want to help our customers. So we are trying to give you the infrastructure with the GPUs that you can use, easy access to images with the most important machine learning engines, from TensorFlow to Apache Imagenet to PyTorch and so on. And using these tools, we have seen customers doing amazing things. This is the University of Stanford, and they build an engine to help the early detection of diabetic complications. So one of the problems of diabetics is that you can even reach blindness. And to understand if you have this kind of complication, you need to have a picture of the back of your eye and look for specific structure in the blood vessels. This is something that normally requires a very much skilled doctor, and they created a model that can behave comparable to what a good doctor would do, so that much more people can now do this kind of analysis. This is probably the first FDA-approved use of machine learning in the US. FDA is the Food and Drug Administration. It's Arteris. And they use machine learning to discover early tumors in MRI scans. Moving into lighter topics, this is Huddle, that it's using machine learning to understand the strategy of a sport team and give suggestions on how you do sport. This is probably one of the best engines that currently are available for autonomous driving system. It's called TuSimple. It's in California and China. They are very good in doing this kind of classification during the day and also during the night when you have much, much less data than during the day. And to give you an idea of how this works, this is an example of how they do real-time per-pixel object segmentation. Also, the idea here is that they can classify each pixel in real time to understand which pixels are pixels of the road. And this is the first step to look for objects in the road. And then they use this all together, and this is where you see the real-time pixel segmentation. And then in the bottom, you see the colors, give you an idea of the distance of the objects so that the car can understand where they are. And
sorry, just quick pause. Feel free to stay and listen. But I just wanted to let you know, I'm obligated to say it is the coffee break time now. If people would like to get coffee, the coffee will not go away when the coffee break is over. But just so you know, we're at that time in the schedule.
Sorry, I was pretty
No worries, man. Feel free to continue. But
Thank you.
We will also have a panel at 11, so we'll keep to the schedule. Very pünktlich, as the Germans say.
Okay. So if you want to go, feel free, don't worry. So Wolfram Alpha, maybe you use it directly. You may have used it through the iPhone, because if you ask a complex question to Siri, it's actually asking that to Wolfram Alpha. And I love this use case because it's a question that is very ambiguous. So if you ask to Wolfram Alpha who recorded pet sounds, Wolfram Alpha will understand that this is a music album from the Beach Boys. So usually ambiguity is one of the problems with machine learning, and you can see how Wolfram Alpha can solve this problem. Pinterest can look for similar pictures, so if you see something that you like in a picture, you can get more information. And the idea with AWS is also to create high-level services that any developer can use without the need to know all the details of how machine learning works. So we started with vision and Amazon recognition. So Amazon recognition can analyze pictures and give you lots of information. So this is the object and scene detection. I'm using here not a normal picture. I'm using the Mona Lisa from Leonardo just for fun. And here we can see that in this picture, we can see that it's a human, there's people, a person, it's art, painting, and portrait. Then I stop because the next suggestion would be selfie, because of course this looks like a selfie, but I stopped there. And if we go further, we can do image moderation. This is very useful if you have user-generated content. We can classify the content if it needs moderation with different level of classification depending on the culture, the audience. Of course, the Mona Lisa is okay. We don't need moderation. We can do face analysis, and here we can find the face. So it looks like a face, appears to be female. The age range is 26 to 43 years old. So I looked back into my school books. So this was painted in between 1503, 1506. And Lisa del Giocondo was 27 years old when in 1506, so when the main part of this picture was finished, so within the range. And then there's probably the key of the picture. She is not smiling, but appears to be happy. So this is really the secret of the Gioconda, immediately found by this tool. And then she's not wearing sunglasses or glasses. The eyes are open, the mouth is closed, and she doesn't have a mustache or a beard. And then we also have celebrity recognition. So Lisa del Giocondo is a celebrity, so she was found. We have customers using this to process magazines online and find the people that appears in the pictures. And then there's face comparison. So there's lots of copies of the Mona Lisa. When I was in Madrid last year, I was lucky enough to see the copy that is in El Prado Museum. And apparently this copy was completely disregarded as worthless until 2012. Then they started to recover the painting. They cleaned all the background that was completely black and found these nice landscapes in the style of Leonardo. And now the theory is that this was the very first copy of the Mona Lisa, probably painted by a student of Leonardo, and there's even the possibility that it was painted at the same time as the Mona Lisa. If you look at the perspective, it looks like it was painted a few meters on a side at the same time as the original. And according to Amazon recognition, the face is the same with 98% similarity. So if we go, since it was the first time I was using a picture and not a real photograph, I tried with another picture from Raphael, and of course the face is different, and I didn't find a way to overcome the test. And again, we've seen customers doing amazing things. This is Binder. Binder is a company in the Netherlands, and what they do content management. So normally you upload pictures, then you have to manually tag this picture to describe what's inside the picture, and then the marketing of a company can search for a picture of a guy on a bike with a cloudy sky that they can use maybe for some advertisement. Now they use recognition for auto-labeling the picture, and all their customers, they're super happy because they don't need to do the manual tagging anymore. So after voice, we have speech, and there's Amazon Polly. Amazon Polly is the voice of Alexa, but compared to Alexa, it can talk 25 different languages, including Italian and Korean.
I am so sorry.
I'm too long.
We are a little over time, and we have to prepare for the next talk.
Okay, so I just want to finish this one. And if you want to add voice, it's very easy to an application. And the idea is, as Amazon, we are trying to create high-level APIs that can help everybody add some smartness in their application. Thank you.